Hello there. I just wanted to make a quick video about dataset preparation for training image super resolution models. This is just an example process that I made and that I wanted to show, but I am constantly learning new things, so this process could of course change, but it's just something I wanted to show. Because maybe someone is interested here. Just at the beginning, though, I want to make a section to just update all of you on on what's been happening since I made my last two videos. Of course, this part of the video can outdate fast, so if you want, you can just skip to the other part. But one of the things is SR Former. I talked real quick about it in the last video, or showed a training config about it. Is one of my favorite networks. And what I did is in the GitHub issues, I started posting my trained models for the developers because I thought maybe, they would be happy to see people train and apply their networks and use them. So that's what I did, and they were actually happy, and they even mentioned my model in their README. So that was really cool. Another network that came out recently is DOT, Dual Aggregation Transformer, and it is now also one of my favorites. I trained some models for it, and I really like it. And one thing I also like that I wanted to show, because I want to give credit to the developers of those networks, because they do a lot of work and put in a lot of time for us to profit from such cool upscaling networks. And when I actually posted something in the GitHub issues, the developer responded within 15 minutes. So that's crazy. I really do appreciate when developers of such networks stay active, also on their repo, and answer questions of the community. I think that's really cool. I just want to give credit there. So that's something that's really cool. Talking about SR Former and DOT, Chainer just recently implemented support for those. So you can actually run DOT and SR Former now in Chainer. You need to use the nightly version currently, though, the version 0.19.5 nightly, and then you can use those models from that architecture too. And those are two of my favorite networks. Then some other news. The hot upscaling network, something that they did not too long ago, is they released a sharper version of their already released pre-trained model, the real hotgen SRX4 and then sharper. And I wanted to show this real quick. This is just an input image that I took and ran through it. This is just how it would look like if I simply upsample it with cubic 4 times, so we have a comparison. Then this is how it looks like if I use the real hotgen pre-train model. And then this is how it looks like with the newer, sharper model they released. So you can see the books there are sharper. You can also see the columns or the text in the left bottom corner. So there is a sharper version now of the hot model, the real hotgen model. And how they did this is they used the unsharpening mask, set those to true in the real ESRGAN on-the-fly degradation options during training, and this will make the output sharper. Now the thing is, I'm not sure if I would recommend that. Why I'm saying this is because 3 months ago now, so 2 months prior to the sharper model, I did a model I called 2x Lexica RDBNet, which was trained on AI generated images to upscale those, and on the RDBNet network, which simply it's the ESRGAN network or real ESRGAN network, since real is just simply denotes the training pipeline of using on-the-fly degradations during training. So those are all the exact same network. I did, after training this model, I made a sharper version of it, which I simply called -sharp. And the difference there was that I actually set the unsharpening to true. So it's the exact same thing that I had done there just prior. And the thing is, what I wanted to show is this is an upscale with my model, and this is one upscale with the sharper version where I had used unsharpening mask. The thing is, with unsharpening mask though, I feel like it introduces haloing. So if you have a look at the side of the face there, you can see there's something going on here. And I don't like it. You can also see around the edges of the eyes that there's suddenly some halo going on. So I don't like this. I actually recommend another way, not using unsharpening mask during training, to always set those to false for model training, but to instead sharpen the data set prior to actually, for example, with a contrast adaptive high boost filter. That's what I did. And I think it introduces, or I think it gives better results than using unsharpening mask. So I recommend leaving those to false. And that's just my experience. I could be wrong, but that's just what I would recommend. Then other news, 2-Minute Papers had just released a video 2 days ago, which is a great channel. It's really cool. And they talked about GigaGAN. And I simply wanted to add something there to GigaGAN. It's from a paper standpoint, it's interesting, but from a practical standpoint, we talked about it. This is why I have those screenshots. We talked about it in March in the upscaling community, but they never did release any code or any model for us to try. So since we cannot verify their claims, what I wanted to say is we remain skeptical until we have a means of reproducing their results for ourselves. Their upscaling results look amazing, but we have no way of verifying this. In contrast to other networks, like for example StableSR, where they release the code, they release pre-trained models, and they actually provide even Google Colabs and Hugging Face spaces like this website here, where you can simply run their network, their model on your own input, and then make a comparison like here, where I took my own input and ran it through different models, StableSR, SR Former and Het, 4x models, and then I can just compare the outputs for myself. And anybody can do this, of course, not just me. And something else I wanted to show too is on the website papers with code. If you go to the task image super resolution, and you click on latest, you will get the newest networks that have code with it. So as you can see here, DivBeer would be the newest that's just released this week, and it's actually a combination. This one uses a 2-stage process, where one stage actually uses a diffusion model and the second stage actually uses a transformer model. It's currently SwinYAR, but I guess it could be adapted to use any transformer models for upscaling. And you could of course also click on no code, where you just get the latest papers with no code associated for you to try out, but the papers are interesting, so you can also stay up to date for yourself on these networks by using this website and looking for the latest and the no code, reading those or trying those out. And the very last thing I wanted to show is to this morning when I woke up. Before making this video, Mussel had just released his own training code for training upscaling models called NeoSR, where he basically tried to make a version that has cleaner code, isn't such a mess, and tested some things on it while implementing those. So we will certainly give this one a go, and maybe I can do a video later about it once. Anyway, about the dataset preparation part now. What happened is I trained a dot model, and then I wanted to train another dot model, and I thought for my for my data set, I'll just use the FFHQ, the Flickr Faces HQ dataset. So I take input images just from faces to have the model learn to upscale faces specifically. So this is meant as a model to upscale, profile images and such things. And the Flickr HHQ dataset consists of, you can see it here, 70,000 images at 1024 times 1204 resolution, and is around 90 gigabytes size. So I simply downloaded that, made a config, in the input straight up, threw in that dataset, and let it train and checked it with the validation output. And after 50,000 iterations, the results were not to my liking. Let's say that, or I had hoped for better results at that iteration around. And then I started, playing around with the dataset, trying to actually do something with it, prepare it a little bit. I just, looked inside that folder at the first 40 images, and what I saw was, or what caught my eyes were some images that were, super overexposed, or the background actually is blurry and noisy. So if it crops from there for training, this will not be good. I don't want such images in my ground truth folder, to be honest. So I tried around, you can see it here, I tried around with different, preparations, and I made a, dataset preparation process out of it, trying to get better results, hoping to get better results. And I did. What I did is I made another dataset out of it based on this FFHQ, which you can see is just way smaller. It's 10,000 images, 512 by 512 pixel, images, and it went from 90 gigabytes to 4 gigabytes in size. And you can also see I calculated the HyperIQA score, which basically is something that gives a metric or a score. It scores every image based on its quality. It tries to score every image based on its quality. This is the paper to HyperIQA, and I got, I noticed it because I remembered Muzzle talking about it in the Discord prior. So I used that one to filter images out in the process. I will show the process afterwards. I thought I'd show results first, if it really is better or not, if we prepared the dataset. And so I had trained, two models, FFHQ dot and FFHQ-L dot, which also handles noise, which was, meant to handle low quality input images that have noise and blurriness a little bit. And those were the ones I trained on the FFHQ dataset directly. And then I had made the FaceUp dataset, and I retrained, or I trained models again with familiar settings. So I did a FaceUp dot and FaceUp L dot again to handle noise. And then I made a sharper version, but a sharper version without using unsharpening mask, but by sharpening the data input, the input images prior to training, because I wanted to show this because I talked about it previously. So I wanted to show the results real quick. So I hope you can see this in the YouTube video. So this is the input image, input validation image with its original size. And this is how it's, if I just 4x upsample it with cubic again, as a comparison. Then this is what it looks like with the FFHQ dot. This is the model I trained on the dot data set directly. And then after preparing the data set with or making the face up, it looked like this. So if you compare those, you can see, if you look at the nose here, you can see better details. Also at the eyebrows, if you look at those, it's more detail, more skin texture details, and also the hair looks better like this. And then I also made, the sharper version without using unsharpening mask, and this is this one. So you can see a difference again. If you look, at the eyelashes or the eyebrows, it's way sharper, or the lips. I think it increased in sharpness, and I like it better. So that's the difference of, you know, using the dataset and using a prepared dataset, basically. I have another example here. The input, cubic upsampled, you know, FFHQ, FaceUp, and FaceUp sharp. So you can see here again, you know, the skin details on the shoulder and the eyelashes here, for example, and eyebrows, how it increases in detail in my opinion. Then another example, I will post those examples in the description. And then this one is the low quality input model I made, which was meant for images that have noise. There's also hazing going on here. It doesn't handle that, but I can show it better. This is the 4x upsampled version with cubic. You can see all the noise going on here in the background on the wall. Then this is the model trained on FFHQ. You can see it handles. So this is the model I trained for good quality input, and you can see it's not bad, but you can see the noise in the background is still there because it's not made to handle that degree of noise. So this is the low quality input version of FFHQ used directly as dataset. You can see how the wall is smoothed out here. Then the next one is the same thing trained, but with the FaceUp dataset that I made out of FFHQ. If you look at the eyes and eyebrows, you know, it's way better details, and also the lines on the wall there in the back, you can see it's sharper, and also the noise is still removed. And then we have the model, the sharper version of it. This would be the difference to the sharp version of it by using sharpening on the dataset itself. So those were the examples. And now this is the process. I just called it Hillemon's process real quick. Hillemon is just my gamer or Discord tag. My name is Philip and my friends call me Fips. I called it version 1 because this can always change. It's just what I did with FFHQ and used afterwards for tests too. But I'm constantly learning, and I made this video specifically to show this process so that others can then actually, or at least in the Discord community, can then, you know, tell their thoughts about it and what should or could be improved upon it. So this is the process. What I did is I scored, you can see the different steps here. I scored the images, filtered the images, multiscaled and cropped to sub-images, then scored and filtered that again, and basically just redid this whole step until I was satisfied with the images I got, and then simply renamed, created the meta info text, and then applied contrast adaptive high boost filter for the sharp version. But I'm gonna show this process. This doesn't really help this way. So what I did is I made a small dataset. This is actually a dataset of 250 images. What it is it's actually meant for validation. It's the LSD dataset, but I will use it to show the process because 250 images is, you know, small enough so that I can show it without us having to wait long for everything. So this is my dataset. And if you remember, the first step was to score this dataset. So that's what we'll do. I have the command stored here. So first thing we'll do is we will run the HyperIQA scoring on it. So you can simply run that script. And then as you can see here, it will score every image, meaning, yeah, it will just give a score to every image. So after running this, it will have created this Dataset score text file. We're gonna open this with LibreOffice Calc, so we can, you know, more easily sort the scores. So we can, select a specific column and then sort. And then you can see the highest scored image up here. You can, of course, always go and check those if you're interested. For example, this one, you can see no noise going on, pretty sharp. In contrast, the lowest scored image would be 245. So you can also go have a look at this, and you can see there's noise going on, which we don't want. So now what you can do here is you can filter and choose a cutoff point. Now what I recommend is to choose the score, to find the score that's above 0.656. 0.56. So this would be our cutoff point. Anything above we would take, anything below we would throw away in that sense. This is just a score I suggest to take, 0.656. But you can do not only a score-based cutoff, but an image count cutoff. So now in this example, it falls exactly to 180 images, so I will take this. If it would have fallen to some weird number, 138, I would have just gone to 180. Now this is just an example data set, so very, very few images. In the FFHQ data set, which consisted of 70,000 images, I actually would go with around 2,000 images filtered out. So, the score could be higher or lower, but I would go with around 2,000 images filtered out in this step. So what we'll do here is we take all of these image names, copy them, open a new file, a spreadsheet, then copy it into the column. Then I'll type cp for command for copy file or copy to use it in the terminal. And then here we will, since this file will be in the dataset structure, we will go up one folder and then dataset filtered and go into such a folder. Then I'll just extend this, copy it out into a text file, and remove the tabs with spaces. So this can actually be used, replace all, copy this out. And now we have our command. If we go into the folder structure, we need to create this folder called dataset filtered. Yes, then we can go back into your terminal, cd into the dataset, and then paste and execute this. So this should have copied all the files to that filter. It was really fast, but it was only a few images. 2,000, it would take a little bit longer. So now we have our filtered data set. So if we have a look at the steps I said, then we already did step 3. Now, more or less, something you can also do in this step is, this is also why I'm doing it this way. Since we filtered out any image above 180 for our dataset, from this dataset we can actually take, this 10 images, and then from these, take them, copy them out and use them as validation images. Or choose our validation images from those, or from in the FFHQ dataset, I actually took the next 20 images and then manually inspected them, which ones I like to look at, and then copied them into a separate validation folder, so that we could provide our own, our validation images together with this dataset, because you don't want the validation images to be in the training dataset also. So that's a good thing here to do. Now, since we have our filtered images, now we can do multiscale. Why I didn't, skip those 2 steps at the beginning is 2 points. The first point is this allows me to actually create validation images also, instead of, trying to take validation images from already cropped sub-images, but here we still have the high quality or high resolution images. But the second point is also because the LSDR dataset, for example, which I used for such a process as well, already is 150 gigabytes of images. Now, if I multiscale and crop them, it would not only take way longer, but it was also, use way more disk space. So this is why I did it in this step. So the next step is to multiscale this. So we still have our terminal here. I'll need to go up one. I'll clear it. So we have our generate multiscale script here, and we will run this. I have the command ready here. We need to see dataset filtered is what I called it. Really good. And we'll put the output into a folder called dataset filtered multiscale. Yes, so let's run this. And you can see what it does here. It crops. I adjusted the script a little bit so that it will not save output that's actually smaller than 512 by 512 pixels. So sometimes you can see it saves and sometimes it's too small. And you can see this, here in this folder, you can see it creates all the multiscales here, like this. So as an explanation, why are we doing this? Why am I multiscaling is because especially in the FFHQ case, all the faces were around the same size, around, the same distance from the camera, so to say. And then if we use this as a data set, the upscaling, will learn faces from, that distance, so to say, but you could also have images where there are a lot of people in the background, so the faces are way smaller. So we're using multiscale, so the image, so while training it crops and it doesn't always just see, a part of a nose, but the full nose. An example would be you go to a museum or an art gallery maybe, and you look at images, the paintings, and for every painting you always only look at it from very up close. So your nose is almost touching the painting. And every painting you are only allowed to view at this distance. But then you decide for one image to actually take 3 steps back. And then you actually see the image in its entirety. So you get a way better, idea of what the painting looks like actually, if viewed as a whole. But you also, since you were that close, you also know very good, or you have seen the painting brushes, the texture that the brush made when painting this painting. So it gives different perspectives. So this is why I'm multiscaling, because for an upscaling model to learn, maybe a bush up close might look different than a bush from afar in a photo. And I wanted to learn to upscale all of those. So I multiscaled them. You can also have a look here. So the filter data set is around 370 megabytes, and the multiscaled one is now around 595 megabytes. So it increases in size. This is why I didn't do it with the full data set. Then we'll crop those to sub-images. I again should have the command here. So we're going to use the extract sub-images script, dataset filtered multiscale folder as input, and output the dataset filter multiscale sub-imaged folder. So let's run this. No module named basic SR, well then we'll install it. Okay, now we'll retry. And yes, so it creates those cropped images. Now from it, why we do this is to simply increase the input-output speed. So this should speed up training, because during training it will crop the images. So once this is done, we can have a look at it again, just that you see what this looks like. So now we basically have crops. This is what we wanted. You can see it here, just crops out of the images. And now those crops can have, of course, be from different fields in the images. In the examples at the beginning, I showed an image that had blurry, noisy background. So if it's a crop from there, we actually want to score and filter those again. To show the folder size now, it's 1 gigabyte. So this process went from 370 megabytes to 1 gigabyte, and this is now why I said I don't want to use it on the 150 gigabyte input folder right away. That would have blown it up. So now we're gonna score those sub images. Do the same thing again, just with, or I have it here. Save file, sounds good. Okay, once the scoring ran, we can again open the file with LibreOffice. Okay, then we'll sort the scores again and have a look at the lowest scores. Yes, we want, well, you can have a look at it again. It's always good to, visually check those. Let's just search for it, 226T0, S002. So yeah, I guess this image is mostly just monocolor background. This also happens a lot when doing crops. Also, a good idea is to actually, let me go out of this, to sort the images by size. And you can see the, oh no, second worst score. But here, if we sort according to size, we will find such images also, because you can see there's just only monocolor background. So the file almost contains no information, while the biggest size here will contain the most information. We can have a look at this one as well. Yes. So sorting it by size is also not a bad strat. I actually used the combination of, choosing score cutoffs and then having a look at the smallest size again. And if I'm not happy again, I go to repeat the process again. So here I would suggest the same thing. We go to scores 0.656. Yeah, is the cutoff point I normally suggest. Now again, 1874 seems like some random number for me. So we could either increase this to maybe, or decrease this. Let's go with, since it's small sample, no, let's go with 1800. So this sounds like a good number, and the score is also not bad. So we'll, do the same thing here again. I'll speed this up. So we have the images in here. We can go have a look. We can sort by size again. Let's have a look at the lowest size. This is actually, there's still a lot of, monocolor in the background, but I don't think it's bad. These do not look bad, to be honest. Now, this doesn't look bad, to be honest. Now, I repeated this process I believe around 3 times with the FFHQ dataset. But yeah, I'll do it again here. I'll increase the threshold size if this is the correct one. That's at filter multiscale. Yeah, I'll go with 1500 in this example. Yes. Speed it up again. Okay, then I will have a look at the lowest sized file here again. Might be still the same one, yes. So yeah, so this didn't do much, but when I did it on, you know, the FFHQ dataset, maybe I can show it here. You know, I would use the, or not, maybe here. Yeah, first I would use the top 25K images, but then I wasn't happy with the result, so I lowered to top 15K images, and then the lowest size image still wasn't good enough, and then I went with top 10K, and then I was actually happy. So I used 10,000 images, or the 10,000 best sub-images from FFHQ for the FaceUp dataset, and this time I will use the, you know, top 15 or top 1,500 crops for this dataset. So now you can see we did it here, and you know, you can repeat the step on as often as you'd like. I just did it 2 times here, but just because I lowered it a little bit by 200 images. In a bigger data set, this would make more sense to actually repeat this step until you're happy. If you're satisfied, you can just, of course, not repeat it. Now we're simply going to rename those images because you can see here they have some, you know, weird names. We're actually going to also rename this folder to dataset final, whatever name you would give your dataset that you created. I'm going to use car rename and then simply add this folder. 1,500 folders. So we're going to rename those and just, you know, with numbers. So that should be cleaner. If we sort by name, yeah, I like this better. So we're going to create, after renaming, we're going to create the meta info file. I have the command still here, and we're going to copy this in. And now we have a meta info file that contains all the file names that we can use in training. And you know, this together with this would be our final data set. Now something else you can do is to apply the high boost filter. That's what I did to create the sharper, you know, models without using the unsharpening mask. And what I did is I simply opened Chainer. And then in here, you can use the image file iterator and then, you know, choose that folder here, dataset final. And then we're going to take the image and apply the high boost filter with amount of 2 with using contrast adaptive with contrast bias of 2, and then simply, you know, save the image and maybe save it in a different folder. So yes, use the same image name, and then we can just simply run this. So after having done this, we will actually have now the final data set together with the meta info that you can use for training a model, or the dataset final sharp that you can use for training a sharper model without using unsharpening mask. Together with the meta info, we can still use the same one because the file names didn't change. So yeah, that's all that I wanted to show. Hope this helps, and thank you for watching. And if there's, any improvements or new things, then I could maybe write it in the video description, or then maybe later once make another video. So thank you for watching.